So this is our third lesson. The first two lessons we looked at differentiating the exponential function and also differentiating the ln function, which is what we did last time. So this time we're going to integrate to get to the ln function. So last lesson I would have asked you something like, what is the differential of the ln of 3x plus 5? So you say the differential of 3x plus 5 is 3. Write it over the original, so 3 over 3x plus 5. Oops, and we can just check that is the right answer. There we go. So, the type of question I'm going to be asking today is the reverse of that. So, what is the integral of 3 over 3x plus 5? Now, that's clearly what this is. So, the answer must be the ln of 3x plus 5, but don't forget something important when you integrate as well, plus c as well. Now, notice one other thing that I included in my answer here as well. I also included absolute values. Now, why did I do that? Remember, when we do the ln function, we're not allowed any negative values. So to get around that problem, I've put the absolute value here. So one of the things we're looking for in today's question is the top the differential of the bottom? If it is, then we can say it's the ln of the bottom plus c. So that's something that we're going to be keeping our eye out for. So if I gave this question 4 over 4x minus 3, differential of 4x minus 3 is 4. Aha, therefore this must be the ln of 4x minus 3. Now, I understand why people get confused with this, because we're doing an integration question here, but what was the first thing I actually did was, I did a differential. What was the differential of this? So that's something you've got to just get your head around while you're doing these questions. Now, this time, 12 over 4x minus 3. Differential of 4x minus 3 is 4. So it's not 12, but it's pretty close. So what we're going to do is we're going to fix this question. We want the top to be 4, but I can't just put 4. But I can say 3 times 4 is 12. So I can bring the 3 to the front of the integral. Now I actually know what this integral is because it's the same one as this. The top is the differential of the bottom. So I can say it's the ln of the bottom plus c. So sometimes we just have to fix the question a little bit to make sure this works. So for example, this had been 8. What I would have said is I would have still left this as 4, but then I would have put a 2 at the front because 2 times 4 is 8. Or alternatively, I guess if this was just 2, then I'd still want 4 at the start, and I could say a half of 4 is 2, and I could put a half at the start of this question. Which is actually what the last one example was. If I do a half of 4, I get 2, but I want to make sure the top is the differential of the bottom. So I can say, and that says plus c at the end, that it's the ln of something. Okay, this time, let's take a little look at this. If we differentiate this, differential of x squared is 2x, differential of 2 is 0, so 2x plus 0 is 2x. So perfect, the top is the differential of the bottom, so I can just say it's the ln of the bottom plus c. And don't forget the absolute value lines. This time, differential of x squared is 2x. Notice it's the same question on the denominator, so I got 2x. Now, the problem I got at the top is I got negative 14x, so I want it to be 2x. But I've got to fix this a little bit. So what do I times 2x by to give me negative 14x? And the answer is going to be negative 7. And therefore now I can write out the answer to this question. As the top is the differential of the bottom, I can say it's the ln of the bottom plus c. And notice I got my negative 7 at the start as well. So it's just a little bit of fixing for these questions. I chose the same thing again for the denominator here, so we got 2x. What I really want is x. So what do I times 2x by to get x? Well, actually I just do a half of that number. So if I bring a half to the front of the integral, oops, that shouldn't be there. It should be a half of this. And therefore we can say it's a half ln of x squared plus 2 plus c. So, just a little bit of manipulation when you're doing these questions. But when you see fractions and it's an integration question, that should be your first check. Is the top the differential of the bottom? Or if not, can we make it so? Okay, let's go to an extension question here. So, the region under the graph where the equation y equals 1 over the square root of 2x minus 1 is rotated through 4 right angles about the x-axis to form a solid. Find the volume between 3 and 8. So we can see it's rotated about the x-axis, so that's going to be important. So we're going to be using pi y squared dx. We have our two limits here, 3 and 8. And also I know for this question this is an integration question as well. So we should be able to set up our equation. Pi y squared dx for volumes around the x-axis. We've got our two limits, 8 and 3. We've got to do this squared. Now 1 squared is 1. And if I do the square root of 2x minus 1 squared, I get 2x minus 1. And then I've got to integrate this. Now I couldn't have asked you this question originally when we did this in chapter 17, because you wouldn't have been able to work out this integral. But now we can. So one thing we should check is the top the differential of the bottom? So the differential of 2x minus 1 is 2. So not quite. What I was hoping for was this. But can I fix this to make it look like this? Sure. What do I do to the 2 to get 1? Well, if I do a half of 2, then that would give me 1. So I can actually go ahead and actually work out the answer to this question. And that's exactly what I did here. So a half times by pi is pi over 2, and then now I can go ahead and work out this integral. So as the top is the differential of the bottom, I can say it's the ln of the bottom. So the ln of 2x minus 1. This time I didn't put plus c, because I actually have my definite integral here, and I got my limits. We can go ahead and plug in our limits. 2 times 8 minus 1 is 15. 2 times 3 minus 1 is 5. And we can actually use our rules of logs here rather than using a calculator as well. So we can say it's the log of 15 over 5 or the log of 3. And that would be our most accurate answer. So you can also see now how questions can start to be extended a little bit. When we're doing integration questions, remember the applications from AICE 1 could be area under a curve, or it could possibly be volumes of revolution as well. So that's the sort of extension we're going to be looking at, but with these more complicated integrals.